What's up YouTube? Welcome back to Everything Engineering. Today we are going to be looking at finite element analysis, and we're going to be deriving the stiffness matrix K. So if you look down here, we got this classic truss example. We got three elements. We got a fixed support, a hinge at node 3, and a pin support at node 2. So if we could isolate this bar segment and examine it further, we can look at, we see we got a fixed support, we got a fixed pin support, just like structural analysis, with a modulus of elasticity E, length L, and a cross-sectional area of A. So in finite element analysis, we're looking at 1D movement, one-dimensional movement, and an idealization or an analogy created basically is that of a spring. So we've said that this can be equivalent to the spring with two nodes in this case. And by node I mean, some kind of connection, a hinge or a support, or anything that would disrupt or create some kind of discontinuity in our structure. So basically right here we've got a spring, and we all know that every spring has a spring constant K. And in this case, now that we've defined this spring to be an analogy of a bar segment with a modulus of elasticity, a length, and an area, if you'll recall, looking at our stress-strain diagram, we have linear movement between our stress and our strain, and that's the same as our F equals Kx, our force of our spring, right? K being the spring constant, x being the distance, and the force being the force required to move each node a distance from its origin. U1 and U2 can just be some arbitrary distance moved by some applied force. So from this diagram we know that E is equal to the sigma over strain, Fa over delta L over L. So this is our strain, this is our stress. Therefore, we've arranged this formula such that we've said that our Ea over L is equal to F over delta L. So the significance of that, if you look over here, remember we said that force equal to K times X, so that can also be written as force is equal to K delta L. So looking down here, we've just said Ea over L is equal to our spring constant K. So that's where the analogy came from with the bar segment and the spring. So we've said that the cross-sectional properties and the material properties of our bar is actually equal to our spring constant K. So now let's derive our matrix. So the fundamental formula in finite element analysis basically comes down to just this. And these squiggly brackets are nothing more than just saying that it's a matrix. For whatever reason, the textbooks, or most textbooks and conventions, use a squiggly bracket instead of the normal square bracket, and they reserve the square bracket for the K matrix. Okay, so force applied is the applied force at any one of the nodes shown on your diagram. So here we've got, in this particular segment that we've isolated, we've got node 1 and node 2. So there's going to be a potential to have an F1 and an F2. And then we've got our stiffness matrix, which is nothing more than what we've just proven to be a property of the cross-section and area and length of our bar segment. And then we've got U, which is just what we're going to use as our nodal displacement. So it's going to be just the displacement at each one of the nodes that we'll solve for using the matrix method. So using this formula, this fundamental formula, F equals KU, knowing that K is our stiffness. Okay, so going back to our truss element, or our truss structure here, we can start analyzing this using the stiffness matrix. So we've got different properties. So it's going to be a qualitative analysis, just to prove and define the stiffness matrix. I'm not going to have any values. So if we want to consider, isolate element 1 here. We've got our node, our spring, and our node 2. So we know that there's going to be a potential for displacement 1 and a potential for a displacement 2. And also is equal to K1 times delta L. And our delta L is U1 minus U2. Because if we had springs lined up beside each other in a sequence, say node 1, 2, 3, and we were to apply a force at node 1, it could displace U1. If we were to apply a force at node 1, it would displace a distance of U1. But there's also the potential that node 2 can also displace, right? So the total distance that node 1 would move will be U1 minus U2, because they're not going to be equal, because K1 doesn't necessarily have to equal K2. Therefore U1 does not equal U2. So the difference in U1 to U2 would be the total delta L that this applied force has caused our first element to move, and it will be in direct linear proportion to our spring constant K. So there we go. There's our first equation. Now if we consider node 2, and say we have an applied force on node 2. Same as node 1, I could have a potential for a U1 and a potential for a displacement U2. Using the same argument that we used on node 1, we can say that F2 is equal to K1 times U2 minus U1. This way everything in U2 direction is going to be positive. So by convention, the node that we're analyzing is going to be the one that we want to put first, and this is just how convention and how your teachers will be using it, and it will give us a stiffness matrix that eventually works out in the end with all of our signs. So just know these two formulas. These are important formulas, and this is how a one-dimensional analysis will start, and how you can go by doing your analysis with the matrix method. So just to recap, this truss structure, this is actually a two-dimensional structure, because we're looking at 2 dimensions. It can go in the x and in the y plane. For the purpose of this stiffness matrix derivation, I'm just going to be considering our first element that I've identified here to get our stiffness matrix, and we're not going to look at the 2-dimensional. We're just going to stick with the 1D. So basically now we have these two formulas. These two equations are F1 and F2. So here's our formula: F equals K times U. So now we need to find our matrices. So if we want to put F1 and F2 in a matrix, so here's our two equations. Now from linear algebra, you can recognize these as two equations and two unknowns. Say, for example, if we have all of our properties of our bar given, then we know K1 and K2, for example, and we're trying to look for our U1 and U2 displacement. So looking at this formation, we can easily see that, okay, we can put that in a matrix form, right? So let's put it in a matrix form. And you can look and see that our K1s would be the common factor, and our U1 and U2 would be the unknowns that we're looking for. So if we did this matrix multiplication, we will get those two equations for F1 and F2, right? Because U1 times positive K1 will give us this, plus U2 times negative K1 will give us this, and so forth. So we do know that these are equivalent, and this is what we will get if we did our matrix multiplication. Now, basically, we've solved and created our stiffness matrix. Now, to apply this stiffness matrix to our bar cross sections or any elements, I will be doing an example following this video, but just prove to yourself, A, that these are equivalent, to get a better understanding of how the stiffness matrix works and how we came up with this stiffness matrix. So basically now we've derived the stiffness matrix in one-dimensional analysis. And this can be applied now to multiple nodes in one-dimensional flow of, or one-dimensional forces. And I will be doing an example following this video where we'll be looking at two different cross-sections and an applied force and two fixed ends. So thanks for watching. If you like my videos, like, share, and subscribe, and also check out my website at www.everythingeng.com. And also, let's connect on LinkedIn. Search me up, Blake Tavian. Thanks for watching.